Hey, lesson 5, the Atwood machine. I snuck most of this also into Physics 11. For those of you who are wondering what we mean by an Atwood machine, it says this. An Atwood machine basically consists of a pulley and two weights. We call one of the masses a counterweight. So it's sort of like this, Sarah, except we have to be in our magic physics world now. Are you ready? This pulley has to be frictionless. In real life, that doesn't happen. This pulley can't have any mass, because if it had a lot of mass, it would be tough to move the pulley, and that would change the question. Oh, and our ropes are massless to make the math easy. You can imagine, Ethan, if this was 1 meter long and this was 100 meters long, that 100 meters of rope would actually change the mass on this side quite a bit, and it would be changing the more it fell. We're going to ignore that. So it's kind of an idealized system, a massless, frictionless pulley, massless, frictionless ropes, but it lets us do some really nice questions. Certainly, we use this in real life with friction. Often, an elevator has a system like this, where the counterweight is the same mass as the empty car, and all the motor has to lift then are the people, the passengers. So, the Atwood machine is a pulley system as seen below. The mass M2 makes for it easier for a person or a motor to lift M1. M2 is often called the counterweight. Should be called the countermass, but you know, whatever. Here's our first question. Equal masses are placed on both sides of an Atwood machine. You know what? Like this, these are equal masses. And one mass is lifted higher, like this. If there was no friction here, if this was a massless, frictionless pulley, and I let this mass go, what would happen? Option A, this mass, nothing, system remains at rest. Option B, the higher mass falls down because of gravity. Or option C, the lower mass keeps going lower because of gravity. Okay, so there's the question that we're asking for our Atwood machine. If I raise one mass, and if there's no friction here, there's lots of friction here. If there's no friction here, and I let it go, will it go like this, or nothing? Hey, once again, this gives us a chance to vote. Once again, how high you hold your hand up is how sure you are of the answer. Who says, Mr. Dewick? I think A, nothing happens. Option A, nothing happens. 1, 2, 3, 4, 5, 6, 7, 8. Who says B, Mr. Dewick, that higher mass is going to fall down because like gravity? Who says B? 1. Who says C, the higher mass is going to keep going up? 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. You know what? Before I think about the answer, let's see if we can prove an answer. Because it does say, using principles of physics, explain your answer. I think I can explain this with a good free body diagram. Although, since they gave me this picture on the right, rather than do a completely separate free body diagram, I'm going to label the forces. So, what are the forces on this left-hand mass? Get the obvious one. mg. Normally, if there was two masses, I'd call them m1 and m2, but does it say the masses are identical? Well, then I'll just call them m and m. What else? Tension. Then on the right-hand side, what are the forces? I think that's it on the left. On the right-hand side, what are the forces acting on that mass? Get the obvious one. So we're going to have mg down and tension. Now, most of you voted this one here. I don't know if that's right, but since most of you voted that, I guess if this is accelerating up, which way is this accelerating? Down, which means you're saying this is winner. So let's do that. We're going to call anything that ends up pointing down on the right winner plus. Anything that ends up pointing up, loser minus. So let's start here. We would have mg down minus tension. Now, this tension is pointing up, but Kareem, if you follow it, when it gets to this side, can you see that actually, it'll end up pointing down? It's a loser. And this mg, although it looks like it's pointing down, again, Brian, if you follow it, when it gets to this side, I think it ends up pointing up. I think it's a loser. And that's going to equal m plus m times A. The mass of both times A. Is that all right, Nap? Sorry, what? Did I say this? Second tension ends up being a winner when it comes around. That's what you're saying? Yes, sorry, you're right. Because if I'm doing this right, these should be relaxing, not stressful. Wait. Even stranger. First of all, Dylan, on the right-hand side, m plus m is 2m, and then the A drops down. What do you get on the left-hand side? Pardon me? Everything cancels. So as a number, what's left there? Now, the only way I can get 0 is if the mass is 0. No, the mass is not 0. Or, okay. So now that we've proved that that must be the case, what's the correct answer? A, B, or C? It has to be A. There's nothing to make it accelerate. So B and C can't happen. You okay with that? So those 8 of you that voted A, well done. And then where it says explain your answer, that would be a beautiful proof. No English, good physics, a free body diagram, and an equation. Oh, that would make my little math nerd heart go pitter-pat. Is that all right? After I botched that explanation there, fix that. Okay. You know what? Let's do one with some numbers. So here's a classic Atwood machine. I would have given you something like this in Physics 11. Physics 12, the twist, will be the very last question we do today. But for now, Physics 11, it says, here's an Atwood machine. Mass 2 is 5.8 kilograms. Mass 1 is 2.3 kilograms. Find the acceleration, find the tension. Okay. Let's label our diagram. M1, what are the forces acting on mass 1? Get the obvious one, John. And I'll call that M1G. John, is there a normal force here, or did I make it clear that it's not touching the surface? Okay, if it was touching the surface, I would have a normal force pointing up, and I have to deal with it. Okay. What else? Yep. Anything else? I think that's it. On the right-hand mass, keep going. M2G and tension. The other thing I have to be able to figure out is which way this thing is accelerating. Who's winning? And the answer is pretty simple. Bigger mass. Which mass is bigger, mass 1 or mass 2, according to this question? So if you want to, you can draw a little arrow reminding yourself it's going that way. You don't have to, but just so you don't suddenly forget. Or, you know what? Here's what I would really say. Who's winning? That's the mass. Which force is winning? I'm being fussy. There's no M2 labeled on this diagram. That's not what you called that force. What did you call that force? M2G. Yes? So now, anything that ends up pointing down on this side is going to be winner plus. Anything that ends up pointing up on this side is going to be loser minus. And this is why, Sarah, we decided at the beginning of this unit not to always let down be negative and up be positive. Because here, I got stuff moving both ways. Let positive be what's mathematically nice. And in this case, winner. Minus tension, yes? And then this second tension, when you follow it all the way around, it ends up pointing down when it gets to this side, which makes it a winner plus. And that M1G, although initially it looks like it's pointing down in the winner direction, again, if you follow it all the way around, I think it ends up pointing up. Loser. John, what's that going to equal? M1 plus M2 times A, or M all times A. How do I know? Because I have more than one force from more than one mass on the left. I better have more than one mass on the right. John, you have a stressful day? Need to relax a little bit? Well, I'm glad that I can help you out. Tension goes. Hey, how would I get the A by itself, my friend? It's going to be M2G minus M1G all over M1 plus M2. Now let's plug in numbers. Common mistakes I see here, Nat, kids put the wrong mass in the wrong place. Don't, is all I can say. The other common mistake I see, for some reason, instead of putting a plus sign here, kids think ML means multiply. No, the mass of everything would be add the masses. Don't do that. But now it's plug and chug. It's going to be 5.8 times 9.8 minus 2.3 times 9.8 all over 2.3 plus 5.8. I would encourage all of you to try this on your calculator. This is one I see a lot of kids have all the right numbers on the test, and then they can't get the right answer because they haven't figured out how the brackets work. So I'm going to strongly encourage you to. And I think you get 4.2. Oh, built-in error check, by the way. Suppose you cut the rope for mass 2. What's the fastest it could possibly accelerate at if it was in free fall? 9.8. Is it in free fall? So you have to get an answer less than 9.8. So there's a bit of a built-in error check there. If you get an answer bigger than 9.8, you typo on your calculator, almost certainly. I got 4.2345, that there. I'm going to write 4.23. 4.23 what? Meters per second squared. The other thing someone asked me earlier today, Mr. Duick, acceleration is a vector. Shouldn't you have a direction? The problem is up and down, depends which mass you're talking about. So I'm only really targeting the magnitude of the acceleration. Is that okay? Sarah, what's B want me to find? You notice there's tension in either mass. I could use either mass. I'm lazy. I'm going to use the mass where tension is winning because it's easier to get the T by itself. Which mass is tension winning in? Yeah, mass 1, because tension is pointing up, mass 1 is accelerating up, mass 1, tension winning. So my equation for tension is going to be winner minus loser, tension minus M1G, and that's going to equal M1A. Not both this time. We're only looking at one mass. How would I get the T by itself, Michael? So it's going to be M1G plus M1A, or M1A plus M1G. For A, I'm going to use my answer button, so I'm going to write 2.3, right, Mr. Duick? 2.3, yeah. 2.3 times 9.8 minus 2.3 times 4.23. I'll write the 4.23, but you know me, I like to use my answer button. 2 point plus, yes, you're right, thank you. 2.3 times 9.8 plus 2.3 times, answer button. And I get 32.3 newtons. Mr. Duick, what if I use the other mass? You could have. There you would have had gravity minus tension equals ma. You would end up going gravity 5.8 times 9.8 minus 5.8 times 4.23, and you also get 32.3 newtons. I've rounded off, so I didn't use my answer button, but you get the same tension. Doesn't matter which one. Pick the easier one. Turn the page. This method, Courtney, that I've given you of Newton's laws, a good free body diagram, and then setting up our tug of war is very powerful. So here's a little thought question. It says this: consider the following system. Which of the following is the best force diagram for mass M2? I guess we're sitting on ice, no friction, and someone is pushing on mass 1, and mass 1 is pushing into mass 2, and so I guess both of these are accelerating to the right. Which of the following is the best force diagram? You know, I think the way to answer this is to actually do the diagram. So, what are the forces acting on mass 2? Get the obvious one. Does that eliminate any wrong answers? Nope. Is it sinking into the ground? Is it flying into the... No, okay, so we have normal force. I'll call it normal force number 2 to go with mass number 2. Which way is this accelerating? So there has to be a force pointing. Which force is that? Now, ready? Why can't it be this? And it's stupidly obvious, so obvious that it's tough. You know why it can't be force F? Because force F isn't touching M2. Don't magically start transporting forces through matter. So I'm going to come back to this by doing the free body diagram on mass 1. I'm going to change colors. What are the forces acting on mass 1? Get the obvious one. What else? Normal force number 1. What else? We have an applied force pushing it to the right. And then it's running into this force here, this mass here. When you run into a mass, when you push against a mass, what does that mass do? Okay, we're going to give this a special name. I'm going to call it FC for F, contact, the contact force. The force where those two objects come in contact. I thought about also calling it a normal force because it is two surfaces, but that's too many normals to keep track of. And I thought, oh, they're pushing against each other. Contact force. Oh, and you know what? Forces come in. So if the M2 pushes back on M1 with a contact force, what does M1 do? Pushes on M2 with a contact force. This mystery force here is the contact force, and it's the same length as that other contact force. So the red forces are the correct free body diagram. A, B, C, or D? The red forces are the correct free body diagram. A, B, C, or D? There's no D. Seeing if you're paying attention. It says, explain your answer. I think that lovely free body diagram does the trick for me. Yeah. Quick look at money. Next time, go during lunch. Okay. Is that all right? In fact, we can actually now take this one step further. Let's solve something with people pushing on either end. No friction. We could even add friction if we needed to. We just have a couple of friction forces in the diagram as well. But example 4 says, find the acceleration of the system and find the contact force between the two blocks. Okay. This is a job for a good free body diagram. I'll do the 6 kilogram mass in blue. What are the forces acting on the 6 kilogram mass? Get the obvious one. I agree. M1G. Normal force number 1. Oh, I guess we have, Marcus, applied force number 1, because I think there's 2 applied forces, one to the right and one to the left. And then, is this 6 kilogram mass pushing against the 8.25? Then what's the 8.25 doing? And so that's going to be here, there's going to be a contact force to the left. Okay? Exerted by the 8.25, felt by the 6. What about the 8.25? What are the forces acting on it? Get the obvious one. M2G. Normal force number 2. There's an applied force number 2. Is the 8.25 pushing against the 6? Yep. What's the 6 doing? Pushing right back. Forces come in pairs. So there's also going to be a contact force. Mr. Duick, will these end up canceling out like tension? Maybe. And then maybe to find the contact force, we might look at one mass like we did for tension. Let's find out. Which way do you think this thing is going to slide? I heard someone say left, I heard someone say right. The good news is one of you is correct. Yeah, I think the 42.5 is so much bigger than the 6.75. The 42.5 newtons is going to dominate. Which way is it going to accelerate then? To the... By the way, now if there was friction, I would have friction pointing to the left for both blocks. Be easy enough to add in. Just be a longer equation. So who's winning? To the right. Now, Yesterday I said we're going to walk along the rope. Today I'm going to say we're going to walk along the horizontal. Okay. So, winning, F applied to, sorry, that's wrong, Mr. Dewick. That's totally wrong. I got it pointing in the wrong direction. What did we say was going to be winning? Anything pointing to the right. This is pointing to the, you know why? I covered up the arrow. That was really sloppy of me. I should never have done that. I should have put that arrow higher so I don't cover it up. I think F applied 1 is winning. So let's start on the left and work our way all the way across. So we're going to have F applied 1 is winner. Then I run into this contact force here. Winner or loser? Minus. These are vertical. I'm going to ignore them. These are vertical. I'm going to ignore them. Oh, then I run into a plus contact force to the right. And then I have a minus F applied number 2. What's that going to equal? Yeah. M1 plus M2 times A, or M all times A. Cool. In fact, you get actually a pretty clean equation. How would I get the A by itself? And I'm going to start plugging in numbers right now. It's going to be 42.5 minus 6.75 divided by 6 plus 8.25. Do that one in your head, Mr. Dewick. 14.25 dividing by that. I got no tricks for that. I got to go to a calculator. 42, bracket, 42.5 minus 6.75 divided by 14.25. And I get an acceleration of 2.51. We're not done. It said it wanted us to find the acceleration. Check. What else did it want us to find? Okay. Much like tension, we're going to go look at one mass. Which mass will be easier to... Oh, you know what? Wherever the contact force is pointing in the winning direction. Is the contact force pointing in the winning direction on the 6 kilogram or on the 8.25 kilogram? I'm going to use the 8.25. I'm going to say to myself, contact minus 6.75 equals M2A. Hey, this is kind of nice. Contact is going to be M2A plus 6.75. M2, 8.25. A, still in my calculator, plus 6.75. 27.4. Last class, somebody said, Mr. Dewick, what if you did it with the 42.5? I did it really quickly. I went 42.5 minus contact force equals M1A, got the contact force by itself, and we also got 27.4. Doesn't matter which one you pick. Newtons. So that's sort of a little bit new, physics 12E-ish, except I would argue, Taylor, I didn't do anything new there. I had to be a bit more careful in my free body diagram, but once I figured it out, it was still Newton's laws, still one equation, and away we went. Is that all right? Example 5. Example 5. A curling rock, rock number 1 right there, is traveling due east across a sheet of frictionless ice. And this is a top view. You're looking down at it from above, like when you're watching curling on TV. It collides with rock number 2, and rock number 2 briefly exerts a force due north. After the collision, what path is the correct path of rock 1? Path A, path B, path C, or path D? Once again, we get to vote. Once again, how high you hold your hand up is how sure you are of the answer. So again, what we're saying is this rock is standing still. This rock comes along. It experiences a brief force to the north. How will rock number 1 move after the collision? Not during the collision, after the collision. What path will it be tracing out? Who says A, Mr. Duke? A. Who says B? Who says C? Who says D? Who's right? Keep your hands up. You love Dylan walking in, looking at the peer pressure, hasn't even read the question, but he's putting his hands up with everybody else. Convince me. Why? I would say this. After collision, no force. And if there's after the collision, there's no force acting on it because you're on ice. If there's no force acting on you, how must you travel? In a straight line. Newton's first. Newton's first. Another thought experiment. Example 6. Suppose you take a water bottle and you drill it with many small holes so that it leaks. If you drop the water bottle while the water bottle is in free fall, what happens to the leaks? Will it A, stop leaking out completely, B, leak out at the same rate, C, leak out at a slower rate, or D, leak out even faster? Let's vote. Who says, Mr. Duick, A, the water's going to stop leaking out totally? 1? Was that a hand up, Twitch, or not? Oh, okay. 1, 2, 3, 4, 5. Who says B, no change, is going to keep leaking out at the same rate, Mr. Duick? B. Who says C, it's going to leak out but slower? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Who says D, the water's going to leak out faster? Psst, psst. No one. 19 of you voted. Everybody raise your hand. Serious. Everyone raise your hand. Everyone raise your hand. Who would like to do the experiment? All of you? Okay, we will. Let's pause the video. I need a couple. So what was the correct answer? A? That's interesting. Even more interesting is why? Why? Some of you voted A. Did you think about why? Can you convince me? Or was it a fluke? Derek. Okay, here's what I said. Follow my argument. If I'm dropping the bottle and the water, what's their initial velocity before they start? So they have the same VI, yes? You agree with me? While they're in free fall, if I ignore air resistance, and even if I don't apparently, what's their acceleration on the bottle while it's in free fall? Do the math in your head, you know this. 9.8. What's the acceleration of the water? 9.8. If both the water and the bottle have the same VI and they have the same A, can their distances ever be different from each other? Is it ever possible for the water to get ahead of the bottle or behind the bottle or leak? No. Is that okay? So let's write this. I think in my explanation, I'm going to say same VI and A, therefore same D. I would totally take your answer, Derek. I wanted to think of a shorter way to write it. There you go. A couple of words. Yeah? One more and we're done. Here's Physics 12. I wrote here start recording because I forgot to start recording in my last lesson, and so I had pause. Those of you that are wondering on YouTube, if you're wondering why the numbers here change, it's because I'm doing a second class. What am I asking you to find in example 7? Mass. Last year in Physics 11, I said if I give you both masses, find the acceleration, find the tension. Physics 12, if I give you the acceleration or the tension, find the missing mass. I'll give you one mass, find the other one. That's Physics 12. If I've done this right partway through, you'll go, okay, so they want me to find a mystery mass. Guess how I'm going to start out? Yeah, let's label my forces. So it looks like I have M1G tension, right? M2G tension. I need one more piece of information. For me to find the mystery mass, they have to tell me which way things are accelerating. Did they tell me which way things are accelerating in the question? Which one's downwards? Because one's always going up and one's always going down. Mass number 2. Okay, so we're accelerating that way. Here's my argument. If I gave you both masses, to find the acceleration, you would write a great big mass equation, and then to find tension, you would zoom in on one mass. Here, I'm missing a mass, but they gave me the acceleration. I'm going to reverse the procedure. I'm going to start out zooming in on one mass. So first of all, let's try writing an equation for the mystery mass for mass 1. Which way is mass 1 accelerating? If mass 2 is accelerating down, which way is mass 1 accelerating? So here, who's winning? Who's losing? Okay, so I'm going to have this. Tension minus M1G equals M1A. Now, I want to find M1. Do I know A? Did they tell me that in the question? Cool. Do I know G? Oh, great. Do I know the tension? Oh, I can't. Hey, over here, let's write an equation for this mass. For this mass, for mass 2, who's winning? M2G minus tension equals M2A. And that tension is the same as the missing tension that I need to find the missing mass. Let's find this tension. Let's get this T by itself. We've done this dance before. It's going to be M2G minus M2A equals tension. Do I know M2? Yeah. Do I know G? Yeah. Did they tell me A? They have to. Or they can tell you the tension, in which case you would have to find A using this equation and then move the A down to here. Let's get the tension. You know what? It's getting late. I'm going to go straight to numbers. What was mass 2? 8.4 times 9.8 minus 8.4 times 3.5. And I get that the tension is 52.92. And since I'm going to use this to find other stuff, I'm not going to round off at all. I'm going to move that down to there. This has all been the setup. Shayna, what are they asking me to find? Which one? How many M1s do I have in this equation? Yeah, you. 2. How many would I prefer? You know what? Let's get them to the same side. I can do that. I'll plus it over. Yes? I get this. M1G plus M1A, or M1A plus M1G. I don't care which way you write it. How many masses do I have? How many would I prefer? You know what would be really cool? It would be really cool if there's a grade 9 mathematical operation that I could pull out of my back pocket and change this from 2 M's to 1 M. And there is! Anybody know? Greatest common factor. Is there an M1 in everything? On the right-hand side? I can factor it out. I can write this as M1 bracket G plus A. Can I not? Hey, Shana, how many M's are there now? Oh. How to get the M by itself now? Oh. Piece of cake. Now I'm going to pause. Have I really done anything new with you? Or hopefully if I set you guys up right, partway along the way you're going, yeah, I probably could have figured that out on my own if I had to. It's going to be M1 over G plus A. Sorry, let's try that again, Mr. Duick. Tension is going to be, so M1 is going to be tension over G plus A. Let's divide properly, right? It's going to be 52.92 all over 9.8 plus, was A 3.5? Thanks for the help. Yes, it was. Thank goodness I was right. So it's going to be this divided by bracket 9.8 plus 3.5. And I get a mass of 3.98 kilograms. Ta-da. What's your homework? So are you going to get a bit of homework this weekend if I want to try avoiding giving you homework on that big long weekend, okay? First of all, you can, if you want to start whittling away at that big ultimate review, you can do any question that doesn't include a ramp or an angle. Having said that, you'll have next weekend to work on it quite a bit, or the weekend after, so I wouldn't freak out. Number one, we already did. Number one says if you throw it upwards. When I threw it upwards, what happened to the leak? Oh, explanation. You know what? Exactly the same as before. They're both starting with the same initial velocity, not 0. They're both still accelerating down. I know they're moving up, but they're accelerating down at 9.8. You can have the same distance no matter what. You can try number 3. Psst. Give me a little elbow for me, Stephen. Help him write down the right questions. Give him a little elbow. He's awake. So circle number 3. Circle number 3. Number 7. Number 8, I haven't done one like this. I know. I guess there's going to be a normal force. What makes this question really nice is that right there. If it's at rest, what's your acceleration? Trust me, then the question falls apart much nicer. 0 times table. Number 9, I'm not assigning. I'm putting a star next to. If you're one of those nerds trying to get 100% in my class, you might want to try number 9. It's a scholarship question. It's nasty. I'll talk about it in a second. And number 10 is totally fair game. Find a mass. In number 9, it's asking you how high mass 1, the lighter mass, will reach when you drop the bigger mass. What you have to take into account, look, is when you drop the heavier mass, watch, the lighter mass, you see it kept going up for a split second, the rope it's going to be in free fall for a split second on the way up. It's not just how far this mass falls. This will have enough velocity to keep going up for a while. You have to calculate that too. See if you can handle it. It's a neat question. Scholarship questions won't be on your test on your written section, and to be honest, they probably won't even make it as a nasty multiple choice because they're usually too long. It's about, 5 minutes left. Sorry, I was hoping to finish a little sooner.